Hey everybody, my name is Matt Cloudo with Ruckus Networks, and I would like to welcome you to the ICX Troubleshooting series. Our goal in this series is to not only make it fun, but educational as well. So please leave a comment and hit the subscribe button and let us know if there's any videos you would like to see. In this video, we're going to cover spanning tree loops. We'll not only troubleshoot, but also show you ways to prevent them in the future. All right, let's get started. So looking at our topology, we have an ISP router, a core router, we have two distribution routers, and then below that, we have two IDF or access switches. Now in this environment, we're actually concerned with the distribution switches and the IDF switches as well, which is where our loop is happening. Even though they are depicted on our topology, the ISP router and the core router won't be used at this time. Now, the reason for that is because of the way that our VLANs are built. And if we take a look at our topology and we look at distro 1 and distro 2, we can see that we have a total of 6 VLANs built. We have VLANs 2, 3, 7, 11, 51, and 91. Now the way this is noted on the topology is that your VERP-E master and your root bridge for VLANs 2, 3, and 7 is distribution 1. VLANs 11, 51, and 91 are VERP-E master and root bridge in distro 2. Next, we need to understand what VLANs we have configured and what their purpose is. VLAN 2 is our management VLAN. VLAN 3 and VLAN 7 are used for flexible authentication. VLAN 11 is our data or our user VLAN, which is the VLANs that Windows B and Windows C should be in. VLAN 51 is what we're using for multicast, which will come into play in later videos. Finally, VLAN 91 is our voice VLAN, where our phone should be configured. All right, so let's start poking around. So a couple of things that we want to check right off the bat is we want to make sure that our CPU levels aren't super high, and also we want to make sure that all of our interfaces in the devices are up. So as we know, we're in distro 1, and as you can see in the Secure CRT tab, that I'm on distro 1 as well. The host names also match. So let's make sure that we don't have a high CPU condition, and also let's ensure that all of our interfaces are up. Okay, our CPU is high, but it's not at 99%. And the reason for that is that we're in a lab. There's only a couple of hosts attached. There's not a lot of broadcast traffic. That's also a good thing because that means that as we type commands into the console, the devices will respond. Okay, in distro 1, we know our CPU is high. Now let's check in distro 2 and see what our CPU is doing there. Same condition. Okay, our CPU is high, but that doesn't necessarily mean that we have a spanning tree loop. A couple of things we can look at is we can check the interfaces and ensure that everything is up. Okay, all of our interfaces are up. Now, the other thing that we can look at as well is we can check the interface statistics and see how much traffic we have. Okay, we have a lot of traffic, and this is telling me right away that we have a broadcast storm. All right, you might be thinking, hey, Matt, that's a pretty big assumption. We've looked at interface statistics, we've got high CPU, you see your interface stats. Well, our distribution routers are actually doing the heavy lifting in this environment. So if we're seeing that much traffic, and especially in an environment this small with this few hosts attached to it, it's a pretty safe assumption to say we probably have a loop. And since we probably have a loop, let's just fix it real quick. Effective? Yes. Necessary? No. Let's take a look at this and debug it. Now, we know that based on our topology, we have a naturally built loop. We built a loop topology, and spanning tree's job is to basically stop any of those loops from happening so that you have one port that's forwarding and one port that's discarding. And that's not happening right now because we have a loop somewhere in our topology. Now, severing a cable, it has its purpose. If you can't get to the console, if you are at 99% CPU and it's not allowing you to type anything, it's not responding to SSH or Telnet, then sometimes that becomes necessary. However, isolating and fixing the issue becomes much more difficult. Okay, now a couple more things we should look at is we need to check our logs. Those can be pretty informative. So if we do a show log, we see here that we have an entry saying next hop router moved from port 116 to 115, and then again moved from lag 1 to 116, moved from 116 to lag 1. This is most definitely a loop. And the noisiest VLAN right now is VLAN 7. So we have 10.1.7.2, and the way that this topology is built is our VLANs are our third octet and our subnet. So we see this happening all over the place, and we see a lot of transitions in here. There's an awful lot of information in here that's very helpful, but it also helps lead us to believe that yes, we do indeed have a spanning tree loop. Okay, so we're going to use the information that we have in front of us and at least try to isolate what's going on. So I think what we should do is we're in distribution 2 now, and I think what I'd like to do is I'd like to do a debug on this VLAN, which VLAN 7, because this is our third octet. Let's do a debug on this VLAN and see exactly what's going on. Now we're running rapid spanning tree, so we're going to do a debug 802.1w all events VLAN 7. Very likely to happen in a production environment. What I recommend you do is open a separate terminal window, Telnet SSH console, start your debug then, because in a high CPU condition like this, you can very easily lose access to your console. Now, we're in a lab, there's not that much traffic. I'm not necessarily worried about that. I'm just sharing a best practice with you. Okay, so we see some good debug messages here. Now, I'm going to actually stop this. I don't need it to run for a long time. I'm going to type in no debug all, and it's turned off. Okay, so we're going to do this not only in distro 2, but we're going to do it in distro 1. And additionally, we're also going to do this in our IDF switches, and we're going to come back and take a look at the outputs and see what they're telling us. Well, we have some debug output here. And as we're looking at this debug right here is from distro 1. Now, distro 1 is telling us that we can see an RSTP role selection happening. Okay, that's not good. The way that our topology is built, we've established who our root bridges should be. So as we talked about, VLAN 7's root bridge should be here in distribution 1. Now, if we look at this same output again in distro 2, see, we can see the same thing happening. We have a role selection happening. Now let's look at what we see in IDF1. And IDF1 has a lot of transmissions going on. It's sending BPDUs out. Remember, we're only looking at VLAN 7. Now it's not seeing any errors, but it's also seeing topology changes to detect propagating, so it sees everything that's happening up in the distribution layer. Now IDF2, again, we're seeing very similar behavior, and we also see the role selection here. So this is a snapshot of what's happening from a BPDU perspective while the debug is running. Now this isn't isolating or narrowing down our problem. This is showing us that we do indeed have a spanning tree loop, and these messages are proving that. So now we have proof. Let's go ahead and dig a little further. Now we're going to use something called a DM command or diagnostic mode. And what we're going to do is we're going to type dm raw. Okay, correct that. We're going to type dm raw mode brief. And we're also going to type dm raw max of 100. Now if you just type dm raw and fire it off, it's going to continue forever. Okay, so we've set our condition on how we want our DM command to behave, and this will tell us, okay, we're just going to look at a brief view of the packet headers, and then we're also going to stop once we capture 100 of them. This is something we're going to run in every device and then go back and view the output. So once we're done with our conditions, we're just going to execute dm raw, and we'll let this run. Now this will at least tell us what traffic we see, and this is going to help us go back and isolate where our problem is. All right, we have some output. Now we're looking at distro 1 right now. And when I look through this dm raw capture, I'm actually seeing legitimate traffic. This is VRPE, and this is all VRP routers, and we know that VRP uses this multicast address of 224.0.0.2. and its UDP ports, source and destination, is 8888. Now we see that on 114 and 115, 111, 113, so we see this on all of the correct ports. All right, so let's see what we see in distro 2. So if we flip to that tab, now we're seeing some additional traffic in here. We're seeing some IGMP traffic. We're seeing some BPDUs on 111, 113, 115. Now, all of this traffic that we're seeing, including ICMP, all of this appears to be legitimate traffic. And everything that I'm noting here, yeah, this all looks to be normal operation. Now let's take a look here in IDF1 or Access 1. We flip to that tab. Now we see some PIM traffic going on. We see VERP-E traffic. Yeah, we see a lot of traffic here, including OSPF. Now this one is interesting because you wouldn't think that your access switch is running OSPF. However, because of how I have our management VLAN built, we're actually running it here. So we see that, that's normal. All right, we see quite a bit of traffic in here, but it all looks to be, the main thing I'm looking at is I'm trying to check the ports and what I see on ports at this level. So I see all of our traffic communicating on port 1, port 2, port 1, port 22. This is a host, this is our management server. Oh, now this is very interesting here. If you look, you can see that we have a BPDU on port 1111 and also a BPDU on port 1112. So let's take a closer look at this topology and see why that might be happening. Okay, in IDF1, we essentially have 5 interfaces that are right now up. We have our DHCP and Radius server that's attached to 1123. We have Windows B, which is attached to 1124. And then one that's not shown on here is we have our management server, which is on 1122. Now, our uplinks, so in IDF1 going to distro 1, that interface is 111. Now, out of IDF1 going to distro 2, our interface is 112. So we need to look at some things here. Most importantly, I want to see what's happening from a VLAN and a spanning tree perspective. So we looked at VLAN 7. That doesn't necessarily mean that's where our problem is. We're just seeing BPDUs leaving that port that we're concerned about. So I'm going to do a show 8 VLAN 7. And this is right away telling me that we have a problem. Our bridge identifier is noted here as CE20, the last 4 digits. That's also noted on the topology. Now our root bridge identifier matches. And based on how we built this topology, that's not happening. So if we look back at our debug output from earlier, we see those topology changes going on, and that's why, because everybody right now is fighting to be the root bridge, and so we have to figure out what ports are looped and turn that off. Now the joy in troubleshooting is we've got to bounce around a little bit. So what I'm going to do is I'm going to jump back into distro 1 because I'm really curious to see what it's doing. So IDF1 might be the root bridge for the topology. We don't know. We want to make sure that we don't have a conflict. So let's do a show 8 VLAN 7. And oh yeah, see, we have 2 different switches that think they're the root bridge, and that's not good. You only want one root bridge in your topology. So let's go back into IDF1, and I'll just flip to that tab, and we're going to take a look at our statistics. So let's do a show stat. Now, these statistics run from the uptime of the device. So as soon as the device came up, this is when the counter started running. And if you're really kind of curious, over time, I mean, devices run for a long time, we can just do a clear stat, and then we can do a show stat again, and this will give us a really good picture of what's going on. Now, one thing I want to note that's extremely interesting with this is if you look at 1111 and 1112, we can see that those counters are incrementing, but those numbers are very, very similar, and that tells me that that's most likely where our loop is. Okay, so let's recap real quick. We ran a debug because we saw a lot of messages in the log showing that the next hop router was bouncing back and forth between all of the interfaces in distribution 1. So we went ahead and did a debug 8021W all events VLAN 7 and saw the exact behavior that we just proved by looking at our show 8 VLAN 7. We have conflicting traffic out there, or more specifically, we have the inability to come to an agreement on who should be the root bridge because our broadcast traffic and our BPDUs are leaking through our entire topology due to the loop. Then we went ahead and ran a DM raw, and that DM raw allowed us to see what traffic was being transmitted and received on our interfaces, regardless of VLAN or subnet, that allowed us to narrow it down to find 1111 and 1112 as a looped interface. So what we're going to do next is we're actually going to mitigate this and make sure that the loop is turned off and that it doesn't happen again. Because again, these are access switches. These are on the edge. This is where users have the most ability to go in and introduce loops or introduce other types of problems in your environment. We're going to just turn this loop ability off altogether from happening at the edge, and then we'll watch what that behavior does, tweak it a little bit, and then we'll go back and find out why these two ports decided to loop on us. All right, our mitigation tactic, loop detection, and we're also going to turn on air disable, but we're going to adjust how our air disable functions. Another thing I'm going to show you is how to turn on STP BPDU guard on the interfaces so that if it ever does transmit a BPDU, receives it back on itself, it's going to go ahead and shut that port down. We're also going to configure this so that our uplinks don't become air disable in the event of a loop. And we do that because you don't want to isolate a section of your network. Now, a couple things that we're going to look at before we do this is where to actually apply our loop detection. And the only thing loop detection is doing is loop detection basically sends out a loop detect BPDU every so often. When it sends it out, if it does receive it back on the port that it sent it out on, it'll go ahead and start to run through an air disable interfaces because it realizes that it has a loop. Now we're going to apply this only on the two VLANs that would be configured within our user space. So that's VLAN 11 and also VLAN 91. Okay, for starters, we're going to start in distribution 1. And the first thing that I want to do is set up our air disable recovery condition and also the interval. So we're going to do a config T, we're going to type air disable, and then we'll do recovery cause. And if you look at your options, you have all of these different options. So we're not going to go into each one here. We're just going to turn on loop detect, and we're also going to turn this on for BPDU guard. All right, so we have those conditions set. Now we need to set our interval. And what this interval does is it basically says, I'm going to start a timer. As soon as I set a port into air disable state, after this timer expires, I will take it out. If the same condition is seen, I will put it back in, rinse and repeat. So we're going to set our interval to 5 minutes. Now there's another way to take a port out of air disable state. You do config T, go into that interface, manually disable it, and re-enable it, and you're back to normal, assuming you don't have the same condition that's happening. Now, another thing that we're going to do, like I talked about, is we're going to go into each one of our uplinks, or in this case, our downlinks, and we're going to go ahead and turn off the loop detection shutdown disable. That way we don't lose an up or a downlink in these conditions. So I want to go ahead and take a look, and I want to see which interfaces I have. Now, the interesting thing that you're seeing here in distro 1 is because of the loop, we have a lag that's configured between distro 1 and distro 2. That link is currently offline, and if we do a show lag, it's going to show you, oh, it just came back up. So if we do a show FTP neighbor again, it's probably not going to show up again until the FTP packets go back out through that timer, but we're going to enable this on all of our interfaces. So 114 is the interface that goes down to IDF1, 115 goes down to IDF2. So I'm going to go ahead and do interface lag 1, and I'm going to say loop shutdown disable, and that's going to go ahead and enable that on that interface. Now I'll go ahead and do this on interface E114. I'm going to do the same thing, and we'll just tab over so that you can see what we're doing, and that's just a shutdown disable. Do this on E115 as well. Loop shutdown. Okay, we have that configured in distro 1 right now where we want it. Now I'm going to go in and do the exact same thing on distribution 2, IDF 1, and IDF 2. And by doing that, we're going to actually create a catch-all for any loop traffic that will prevent it from looping our entire topology. Now, the other piece of this that we need to cover is we need to turn loop detection on in the VLAN. So if I go into VLAN 11 here, I'm going to say, well, I have to be in config, but I'm going to say VLAN 11 loop, and then I'm going to say, I'm going to actually say loop, not lop. I'm going to do VLAN 91. We'll do the same thing. I almost did the same thing exactly, but we'll say loop. Now, the fun part about this is once you enable this, if you are actually a bridging loop within your topology, you're really upset right now and you're probably booing. Bummer. Okay, so I've got STP BPDU guard enabled on my edge ports in the IDF switches. Additionally, I've configured loop detection in VLAN 11 and VLAN 91, and I've not allowed my uplinks to become disabled. So if we take a look at this and we do a show error disable summary, oh, right there, 1111 immediately, because of BPDU guard, went into error disable. So our loop condition, if we look at our CPU, is now resolved. Now the other cool thing is you can look at your show loop detection status, and it will show you that you have loop detection running on these VLANs. You can see the number of error disables, the sent packets, and the received packets, which is really good to look at. And like we talked about earlier, you can see the loop detection packet interval. It's going to send 1 unit or 10 units every 0.1 seconds just to ensure. So that looks good. Let's make sure that our CPU in distro 2 is back down, which it is. And again, in distro 1, we're going to do the same thing. All right, we look at, so going back into IDF1, I just want to show you here, if I do a show run interface E1111, which is one of our problem ports, we've enabled STP BPDU guard, and it's resolved the issue there. Okay, last but not least, we need to ensure that our rapid spanning tree topology has normalized. So if you remember, we looked at show 8021W VLAN 7 earlier, and if you remember, we had two devices that were battling over the root bridge. They both thought they were the root bridge. That was incorrect. So now when I look at this to tell if our loop has really resolved, then we should have one root port pointing towards the root bridge. We should also have a bridge identifier, which is ourselves, and then we should have a root bridge identifier, which hopefully ends in 6889. Because of the way our topology is built, we know that distro 1 is the root bridge for VLAN 7. And there it is, 6889. Our root port is 111, which is going to our root bridge. That looks great. Now, the last thing that we need to do is we need to go in and resolve whatever's happening with these two ports to ensure that this doesn't happen again. So we noted that 11 and 12 were our problems. So what I want to do is I want to just look at a show VLAN E1111 just to see what VLAN it's in. And I see that it's an untagged port in VLAN 11, or I'm sorry, in VLAN 91. So because of whatever's happening here, I also want to check on port 12, and that's a untagged port in, oh, that's a tagged port in 91. So I think what's happened here is typically if you have an environment where you're allowing one port to be untagged and one port to be tagged, and each of those drops go to an individual's desk, one for a phone, one for a PC. Somebody could very easily go in and plug in both cables into their phone because the phone has a switch connection port and then it has a PC connection port. If that were to happen, this is where you would see that condition. So the way that we can clean this up is just go in and remove the tag and the untagged function on those two ports, and it will normalize this scenario. All right, the final piece of this is we're going to go in and just verify in distro 1, and I would also do this in distro 2, that all of our rapid spanning tree topology is back to normal. So I've done a show 8 VLAN 2. I want to make sure that my root bridge is correct, and in this example it is. I've also done the same thing for VLAN 3. And if we look here, we can see that that's the same thing. Our bridge identifier and root bridge match, which is correct. We are the root bridge for that VLAN. And again, in VLAN 7, we've done that. Same thing, we're the root bridge, that's noted. Now for VLAN 11, our root bridge is distro 2, because we can see that our root bridge identifier and our bridge identifier are different. And if we look at our topology, we can see that 69 Bravo Foxtrot is distro 2, VLAN 91, same thing. So we know that our spanning tree topology is back to where it should be. This issue is resolved, case closed, moving on to the next one. Okay, so we made the problem as small as possible. We troubleshot a VLAN that wasn't even affected. The ports were actually in VLAN 91 on the access switch, but just starting in VLAN 7, it gave us a starting point and allowed us to narrow it down. Now, the real star of the show was the DM raw. That really showed us where the traffic was coming from on each of those interfaces. And that's going to wrap us up on this one. Guys, this was a lot of fun to do. Like I said, please hit the subscribe button, give us a like, and as always, leave a comment. Let us know what kind of scenarios you would like to see built into this series, and we'll be sure to get them added. Thanks for joining us, and we'll see you next time.